we started in Pyrrhus, we weren't really in verification, we were in software simulation. So the last 5-6 years getting into RISC-V, it's back into the verification world. And so what I'm going to talk about today is really the process of verification and also what's evolving in terms of standards around this RISC-V process of verification, and specifically about this RVVI. I'm just going to let this point out. This RVVI-based methodology that we've got here. So, so this is the abstract from that I was asked to talk about here, and it really talks about what we're doing in verification, the different approaches, a lot of the complexity related to functional verification that's coming with RISC-V, and then what's going on in the industry to try and help with reuse and to share things so that we can be more efficient in that. And we've got to consider that with RISC-V, it moves this processor DV task from the tradition, from the IP providers to all SoC developers. And this is a dramatic change where it used to license IP and it would just work. Now you're developing the IP, the processors yourself in the RISC-V world. And it represents a huge migration in responsibility for verification from the IP providers to the end users. And what we're trying to do is work in how to make this more efficient and help people with their time to market with reuse of these. And that's really where this RVVI comes in. So what I'm going to talk about in the next sort of 10-15 minutes is a little bit of background, some of the challenges in there, where RVVI comes in, and we're going to drill down into it and see it in practical use, and then hopefully have some time for some questions in there. So in terms of background, really, traditionally people used to develop SoCs by buying in IP. Now with RISC-V, you can still do that, but most often people are going to RISC-V because they want to extend it in some way. So basically everybody's becoming an architecture licensee, and they've always got to verify it, and that's one of the things that's changed here. And traditionally, if you licensed in some IP, that IP was subject to huge amounts of verification. This is from an ARM blog that I read, where, because basically this methodology is you've got pre-verified blocks that you could integrate them in. And we're going to talk in presentations later from Brecker's talk about integration, verification, and tests and stuff like that. So that's a very traditional part of using IP. But you have to consider that companies like ARM use a huge amount of verification to validate the IP themselves, and that's really the traditional approach. And even with that approach, DV is still one of the huge nightmares in any SoC ASIC project. And this is a Wilson research study from Siemens. That it's still 60 to 70% of the time is verification in these chips. So, and that was when you licensed in a block of IP. And now with everybody becoming an architecture licensee, they're choosing their own instructions, they're changing configurations because there's a huge selection of options that you can choose. And actually you can do a lot of implementation specific. You can decide how something's actually done. So it's not actually defined in the specification. It gives you the freedom to go in your own paths, not just with extensions, but also on the specific implementations, the way registers respond to illegal values and all this sort of stuff. And of course, you've got the ability to add from state. So, you've got a huge amount of verification that needs to be done. And one of the things that people don't realize is that whenever you change something or add an extra option, you almost double the verification. So there's a lot to be learned about process of verification, and there's a lot to be done. And it's changing the way people do things. Now, if we just try and look at how people can do verification, we sort of classify them into really 6 different steps or 6 different approaches. The first 2 really are running programs. Does a program run? Does the program run and get the right results in there? So these are sort of self-testing things. Then you've got the sort of compliance level checking where you can do signature checking or trace logging checking. So these are the approaches that, for example, the signature checking approach, which is the way the RISC-V International's compatibility tests work, is an approach. The ARM tends to, with their compliance checking, use a trace log checking with their ACKs in there. And so this testing there's compliance, and then where we're focused in Imperius is actually on the DV side of things, and that we see this sort of simple sort of step and compare stuff where people are looking at instructions to the full sort of commercial solutions, which are talking about asynchronous and everything. And this is really talking about just dynamic simulation. Obviously, there are formal techniques as well, which are very, very effective in all verification teams use that. But we're just talking here about dynamic verification, simulation. So there's many different approaches in here. And if we look at what we did with Open Hardware, so Open Hardware as an organization, there's a presentation later by Mike Thompson, who's the sort of design as the verification director of Open Hardware. And it was founded about 3 years ago, really to take RISC-V, which is an ISA standard, and exploit the standard and create open source silicon from it with RTL. And one of the key things that Open Hardware set itself up to do was to create the RTL, but to create it at industrial quality levels. And to do that, they engaged with us, Imperius, to help them with the verification of it. And Mike's going to talk about the evolution and how this Core 5 verification testing environment works later. But the first generation of it, was just an overview of it. Is there's a core, there's some peripherals in the test bench, and then there's a reference model. And what would happen is the programs would come in. There were controllers which would step it and compare and run every instruction to the test what was going on, taking into account the debug stuff and the interrupts. And we can see there are really three main components in here. There's the test bench itself, there's the core, and then there's a reference model. Those are the three things. And there are different interfaces that are required. There's one which is the interface between the design under test and the test bench. And then there's the test bench to the reference model as well. So there are two different interfaces. And we can sort of conceptually think about this as the reference model, tracer, the test bench, and the controller. And you need to build a test bench with these in it so that you can do this sort of verification where you load the program up, run it, and you're comparing. As I said here, in these sort of DV approaches, you need some form of lockstepping in there. So, conceptually, you can see the original Open Hardware test bench is looking like that. And if you look at the roadmap that Open Hardware had, yes, it's an open source collaboration, but actually on the roadmap it had 1, 2, 3, 4, 5, 6 or 7 different cores being planned back then. And the challenge is, well, how are we going to actually do the verification of that, where we've got the core and the reference model for the one core, but then there's going to be a second core or a third core, or fourth core. And what's actually going to happen? Are we really going to create different sort of test benches and interfaces for each of these ones? This is a real problem and a challenge in the industry, how this could go forward. And the answer is, of course, we don't want to build bespoke things for each one of these projects. We need standards in there. And why do we need these standards? Well, because there's many blocks that have to be in there. There's many different interfaces. And they're going to come from different suppliers and developers, and they can be used in different projects. And so we need to develop some form of interfaces, some standards, so we can have reuse, common ways of doing things, get projects up and running quickly and be very efficient. So there's a real need for standards here. And this is where this open standard that we created, and it sort of came from the evolution around the Open Hardware projects, but there's some people outside also using it through different companies. And it's the RISC-V verification interface, or RVVI, and it's on a GitHub. And it's to try and standardize the communication between the different components. So from the tracer to the test bench, from the DUT, and to also the verification IP. So there's two main interfaces in here that have been defined. There's the RVVI Trace, which is from the core into the test bench, and it defines information that comes out of this, what we call the tracer. So it's to do with valid instructions and values in the GPRs and things, and also what's going on with the nets. So it also has been defined not only for streaming the data, but also so it can handle the asynchronous parts of the execution as well. And it's defined, as I said, on the GitHub. you can look at the slides later and follow this up. The second API and the second interface really is the API, which goes from the test bench into the sort of verification IP. So it has simple things like stepping and getting values and comparing. So it basically provides a set of standard functions so that any sort of reference IP can be included in it. And it's been defined in such a way that there are C and system verilog versions, so it will work with both commercial simulators and open source simulators in there. And it supports the full asynchronous verification. And so some people say, well, actually, why should we try and use sort of a standard? You know, why should we have RVVI? Well, you have to use some interfaces. You don't really need to invent your own. They don't need to be proprietary. And there's no real downside for adopting somewhere, because we've spent a lot of time flushing this out and making it work. And it was evolved from a previous version, which had already been flushed out around formal. And already it's been used with several different tools and users for several different cores and organizations in commercial and also in open source domain. And so there's some really good benefits in using something like RVVI. And the upsides are that you can pick up tools that work with it. You can gain from experience that other people have used. And these tools can be simple things like sort of reference models, more sophisticated things like verification IP and other components. For example, we're just involved with quite a large project on functional coverage, which just works straight off the RVVI, which is full system verilog from that. And that's a different story there, really. But the key thing is that it hooks the RTL core into the test bench. And it's been designed in such a way that it can handle from simple cores to the most complex ones. So, yeah, in order ones, sure, out of order as well, single issue or multi-issue, single halt or multi-halt, and also all the way through to the asynchronous and all the debug stuff. So it includes everything that's available in the current RISC-V ISO to allow you to basically hook things into it. And it provides technology so you can encapsulate and hook in reference models and also the other components that are using. So the idea is it's about making verification projects more efficient and to make it much easier for people to be able to do verification around the RISC-V processor. And already, as of now, it's been used in several different projects. For example, in open hardware, it's used in 1, 2, 3. 3 of the cores are already using it. Another one's just migrating to use it. And then, it's got a lot of support out from the industry, from people who are involved in the ecosystem, or people who are actually using it for verifying their cores already in their quite a sophisticated level, where they've got multi-core, multi-issue, out of order processes in there. So it's beginning to get quite a lot of support in there, because, as I said, you don't really need to reinvent everything yourself. And for example, from Imperis, just to plug a little bit of what we're doing, is that we've built some technology, some verification IP called Imperis TV, which sits and hooks up to the RVVI Trace to connect this verification IP to the cores, and then it also connects into the reference model and allows it all to be configured. So out of the box, it's very easy to do RISC-V processor verification with a variety of different simulators. And the only bit that you really need to have to worry about is the tracer hooking to this RVVI Trace interface. And then out of the box, this IP can just be used and reused for one project or many projects within your environment. So, really in this short talk, to just sort of wrap it up, I mean, RISC-V is dramatically changing the verification that is needed. It's not just about integration tests, it's about process of verification as well. And it's the biggest change in verification history, really, this migration of this responsibility, because everybody's becoming a processor developer and having to, even if you're licensing an IP, you're going to be extending it. Otherwise, you wouldn't be using RISC-V, really. And so you've got to extend it, so you've got to do the verification of it again. And standards like RVVI enables this reuse and efficiency, so you can get started and run very quickly. And so with that, I think I'm done. So Mike, over to you for questions. Hello.
Hi, Simon. Thank you for that. Mike is we're just transferring the questions to, there you go, there he is.
Hi, yeah, thank you, Simon, for that, and for being so timely as well. We have one question coming in, that's just asking how would somebody get started with this if they're doing their own RISC-V processor and they want to start using RVVI. How would you recommend they go about that, please?
Well, I mean, the first thing is that you need to go to the GitHub, which I mentioned. It's under GitHub, RISC-V verification, RVVI, and have a look at, read through that. And what that does is that allows you to, you can see there, actually, it provides the source of a system Verilog interface so that you can then include that in your test bench. And it defines all of the types of signals that you need to use. Now, and it depends on the type of verification that you're trying to achieve. I mean, it may be that, if you want to do full DV, then you need to license in some technology, for example, like our RISC-V stuff. But if you want to do sort of earlier sort of stuff like Trace King and things like that, you can get the RVVI working, and then you can add a trace component to it. And at the moment, as RVVI is just starting, then there's very little yet available. But you could build a trace and make it publicly available. Anybody could use it. We expect those collaborations to happen. We provide some currently; they're proprietary. But over time, we expect them to be more sort of open and open source. So the first thing you need to do is work out what level of DV you want to do, and then create a tracer which gets the information out of your RTL into the test bench, and then pick up components that can use RVVI. One of the first things that we're making available as Empirus as open source is what we call RISC-V ISA card, which is RISC-V system Verilog source files for RISC-V functional coverage, which will just plug on top of the RVVI interface, and as you're running your simulations, give you functional coverage. But obviously, that requires a system Verilog simulator that has cover points and cover groups. So there's it's early days. The stuff's up on the GitHub. More stuff's coming online. It's already been used in several projects. And obviously, if you're interested in it from a commercial point of view, you need to call someone who's got a commercial solution like Empirus to work with you on it.
Okay, thanks, Simon. One more question as well. Does Verilator support all of the system Verilog features that you use, or do you need to use a commercial simulator?
Yeah, so I mean, yeah, the current state of Verilator, and obviously Verilator has nothing to do with Empirus, but we're actually involved with Chips Alliance that actually is working on this as well as OpenHub involved with Chips Alliance. So Verilator currently supports the Verilog and system Verilog subset that's synthesizable. It does not do today the full system Verilog that's in for test benches, and so today you can't use Verilator for things like system Verilog functional coverage because it does not implement those things. But what I showed on there for our solution in Empirus DV, it actually with RVVI it does hook onto Verilator because there's a C++ interface and a DPI interface, so that you can use RVVI and other downstream components with Verilator. But there is a project in Chips Alliance to evolve Verilator to have system Verilog. But to answer the question directly today, to do full functional verification DV of RISC-V, you need system Verilog capabilities to do with functional coverage and other things, and that does mean a commercial system Verilog simulator. But there's nothing specifically about RVVI. That is, RVVI works with Verilator as well as commercial simulators. But high quality verification is currently only done using commercial verification simulators, okay, Synopsys and Siemens.
Perfect. Okay, that's a good answer. Thank you, Simon. And again, thank you for your talk. And we'll switch over to the next speaker.
Great. Thank you very much, Mike. Thanks.
Thanks, Alan.